Welcome. So we'll be moving to the next topic in this lecture, which is pipelining, right? Pipelining is basically a technique which is used to improve the performance of a system or performance of a computer. Okay, and it is a widely used technique in modern processors. Here performance in the sense, okay, it is basically connected with the processor. We can say that pipelining is a technique which is used to improve the performance of the processor, right? When the processor performance increases, obviously the computer performance will increase. But actually pipelining is directly connected with processor, right? Okay, fine. So how pipelining improves the performance of a system in the sense, actually, or the performance of the processor in the sense, actually it improves the throughput of the processor, right? What is meant by throughput? Throughput is defined as amount of work done in a unit time, or you can say that number of instructions executed per second. Okay, the time can be anything. It can be per second or per millisecond or per nanosecond, right? How many instructions we are executing for a given duration of time. So that is what is called as throughput. Okay, throughput can be improved through pipeline. Okay, throughput can be improved through pipelining, right? See, here there is one catch. Actually pipelining is not going to reduce the amount of time required to execute an instruction. Say for example, there are two systems. There are two systems, okay, two processors. I mean, in different systems, like, okay. Say one of the system, or in one of the system where there is the first processor is there, that is not using pipelining technique. Okay, it is not no pipelining technique. Okay, the second system, it uses pipelining technique. It uses pipelining technique. Okay, but let us assume both the processor speed are same, right? So in the system in which the pipelining concept is not used, here also let us assume that each instruction takes say 2 nanoseconds to complete normally. Okay, in a pipeline system also let us assume that to execute each instruction we need 2 nanosecond. Are you getting? Okay, but if you calculate, so this is the one without pipelining and this is the one with pipelining. Okay, but if you calculate the throughput of this system, the throughput of this system will be better than the throughput of this system. Okay, okay, that is the throughput of this system will be higher. So let us say this system's throughput as TP, throughput of the pipeline system, and let us say this the throughput of this system as TNP, throughput of non-pipeline system. Okay, the throughput of the pipeline system will be greater than the throughput of the non-pipeline system. Okay, that is the number of instructions executed in this system per unit time, in this processor per unit time, will be greater than the number of instructions executed in this processor per unit time. Are you getting? So let us say for example, in one second, how many instructions this processor is going to execute and this processor is going to execute. Now if you see it, for example, if this processor is capable of, I mean, I'm not taking any calculation, simply I'm saying just a example. Okay, if this processor is capable of executing say 50 instructions in 1 second, I mean the one with pipelining, then the other one probably would be executing hardly 20 or 30 instructions per second. Are you getting? Or if this is able to execute 500 instructions per second, probably this will be able to execute 200 instructions per second. Okay, right. So what I am trying to say in the sense, throughput will improve the pipelining will improve the throughput of the system. Pipelining will improve the throughput of the system, but it won't decrease the time required to execute a single instruction. Are you getting? Here also in a non-pipelining system also the time required to execute a single instruction is 2 nanosecond, but here also it remains the same. But pipelining will surely improve the throughput. Okay, for a period of time, if you take the number of instructions that is executed in a pipeline system, it will be more than the non-pipeline system. Okay, okay, fine. Now this is the crux of this topic. Okay, this is the crux of this topic. Now slowly we'll be understanding how this is achieved. Okay, right now probably you may be wondering how it can happen, because we are not reducing the execution time of a single instruction, but when you see the throughput, the number of instructions getting executed is getting more. So how pipelining achieves that? That's what the focus of this topic. Okay, fine. And if you want to perform pipelining in a particular processor, then pipelining requires sophisticated compilation techniques. Okay, that is, uh, say for example, we are talking about execution of program. Programs are executed through what? Compiler. First it will be compiled and then it will be executed. Even if you take an assembly language program, there will be assembler. Okay, in general it can be called as compilers. Okay, so so those compilers should be sophisticated. Okay, so they should be a sophisticated, there should be sophisticated compilers. Okay, then only pipelining is possible. Okay, otherwise pipelining may not be possible. Okay, so so please keep in mind that pipelining expects that the compiler should be sophisticated, or you can call it as optimized compilers, or you can call it as optimized compilers. Okay, these optimized compilers, the sophisticated compilers can also be called as optimized compilers. These optimized compilers, what it will do in the sense, it will rearrange the instructions of the program. The programmer might have returned the instruction in one order, but these optimized compilers will rearrange the instructions of the program in different order in order to improve the performance of the processor, but without compromising the logic. Okay, while reordering, the logic should not be compromised, right? If the logic is compromised, there is no meaning in that, right? So so these optimized compilers will be able to rearrange the program code uh, in order to improve the performance of the processor without compromising the logic. Okay, fine. So now let us try to understand the basic concept of pipelining. Before that, there are there are basically two ways to increase the execution speed of a program. Okay, how can we how can we make the programs execute faster? If you ask this question, there are basically two ways to improve the speed of the execution. Okay, the first method is by using faster circuit technology, especially in the processor and the main memory. That means the technology by which the processor was built, it should be updated. If it is updated, then what will happen? Processor would be able to execute uh, instructions in less amount of time. Previously, if a processor takes 2 nanoseconds to execute an instruction, now after improved circuit technology, that same processor may take 1 nanosecond to execute that instruction, or it may take only 0.5 nanosecond to execute that instruction. Okay, so that is called as improving the performance by improving the circuit technology, or making the programs execute faster by improving the circuit technology. The second method is, the second method, what it says in the sense, but improving the circuit technology, it's not a simple task, right? It is what you call, it is actually in the hands of the designers of the processor, right? The second technique, what it says in the sense, arrange the hardware in such a way that arrange the hardware in such a way that more than one operation can be done at the same time. Okay, the second technique, what it says in the sense, arrange the hardware in such a way that more than one operation can be done in the same time. Okay, by this what happens in the sense, we are not reducing the time required to execute a single instruction, but when you follow this technique, your throughput will improve. Okay, throughput will improve. So the later technique, that is the second technique, okay, arranging the hardware such a way that more than one operation can be executed at the same time. By using this technique, operations per second will not be increased. Okay, operations per second will be increased. Operations per second in the sense, number of tasks completed per second will be increased, even though the elapsed time for one operation is not changed. Okay, so in this technique the number of instructions or number of operations per second will be increased. Okay, but actually the elapsed time to complete one operation will not be changed, right? Okay, so that's the difference between faster circuit technique and arranging faster circuit technology and arranging the hardware in some order so that more than one operation can be done at the same time. So the first technique, what it is doing, it is actually decreasing the elapsed time to perform one operation. But the second technique, it is not doing that. It is just arranging the hardware in a different order so that more than one task can be done at the same time. Okay, so by that what happened, operations per second is nothing but throughput. Operation per second is nothing but throughput got increased, even though there is no change in the elapsed time to 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 perform one operation. Okay, so this is something a clever technique. So we can say that this is a clever technique because we are not changing the technology, circuit technology and all. We are not changing. We are only optimizing the way of utilizing the resources available. Okay. Previously we are using the resource in one way, which is not optimal. Now we are using it in optimal way, right? Okay. Let us see with an example how it actually happens. So, so the concept of pipelining in computers, it comes from the traditional pipelining concept which is used in the real world at several places. For example, in industries there will be pipelining, right? A product, for example, if you take car manufacturing, there may be one unit to prepare the chassis. There may be another unit to connect the chassis and the body, or to attach body over the chassis. Okay, chassis means the skeleton of the car. Okay, to that skeleton this body will be attached, and there will be another unit to attach the engine. Okay, now for example, if all these units work sequentially, then to produce one car itself it may take more time. Okay, but if these units works parallelly not parallelly, if these units works in a pipelined fashion, right? That is assume the first core is entering into the pipeline. Say the first unit is preparing the chassis, so its chassis get prepared. Now the first core move to the second line where body is attached to the chassis. Okay, now the first system is free, that is which is to create the chassis, right? During that time the second core can enter and its chassis can be created. That is, second car's chassis will be created when the first car's body is being attached to the chassis. Are you getting? When the first car's body is done, it will move to the next section where its engine will be connected. Now the second car, by that time it will complete the chassis part will be completed and it will move to the next section where the body will be attached to the chassis. Now the third car will enter into the chassis preparation part. Are you getting? So this is called as this is the traditional way of pipelining. This is how the traditionally pipelining works. Okay, so that concept was borrowed to computer science. Okay, fine. So let us discuss one very basic example with an example of a laundry. Okay, say there are three persons: Anne, Brian, Kathy, and Dave. They each have one load of clothes which is to be washed, dried, and folded. Okay, right? Now say that the washer takes 30 minutes. Okay, there is a unit to wash which takes 30 minutes. There is a unit to dry which takes 40 minutes, and there is a unit to fold which takes 20 minutes. So totally for one load of clothes you need this many time, 30 plus 40 plus 20, which is 90 minutes. Okay, 90 minutes, that is 1.5 hours. Okay, that is to complete this task for one load of clothes, you need 1.5 hours. 1.5 hours. Okay, now there are four loads of clothes. Now there are four loads of clothes. Okay, four persons, so each have one load of clothes. There are four loads of clothes. Okay, now if you do this task sequentially without pipelining, if this task is done without pipelining, then it will take how many hours totally for all the four loads of cloth? For one load it takes 1.5, so two loads it takes 3 hours. For four loads it will take 6 hours. For four loads it will take 6 hours. Okay, if we use pipelining, what will happen, that we will see. Okay, if you use pipelining, then it will be something like this is without pipelining. Okay, once that first load is completed, the second load is started. Once the second load completed, the third load is starting. Once the third load completed, the fourth load starts. Okay, so it takes sequential laundry takes 6 hours for four loads. Okay, if they are pipelined, if they learned pipelining, then how long it would take, that is the question. So actually it would take only 3.5 hours. Okay, so this is how, so this is a good example like how pipeline reduces the throughput. Okay, now you can see the throughput, it is reduced, right? 3.5 hours. You are able to complete four loads in 3.5 hours. Whereas previously four loads were completed in 6 hours. Okay, but have we reduced any of these things? None of these parameters were not reduced. Still washer take 30 minutes, still dryer takes 40 minutes, still folder takes 20 minutes. But we pipelined. How we pipelined? See, after first 30 minutes the washer is free. Okay, so after washing the load 1, the washer can go to wash the load B. Then again by this time it is free, so then it can get into wash the next load. Okay, then it can, by this time washer is again free, then it can get into wash to next load. Are you getting? Similarly dryer is free after this time. Okay, right, so that is after 70 minutes dryer is free, so during this time the next loads dryer can start. Okay, so on and so forth. So this is how the throughput will be increased by using pipelining without reducing the duration of the individual operation. Okay, the individual operations duration is not reduced, but still the throughput has improved. The throughput has improved. Okay, so that's the concept. So exactly how this works, it was explained in this table. You can understand. Say, let us take the this is for load 1. This is for load 1. Say the time started as 10 a.m. or 10 p.m., whatever it may be. Okay, so washing it takes 30 minutes, right? So it is from 10 to if it starts at 10, it will finish at 10:29. Okay, 0 to 29 is 30 minutes, right? Then drying take 40 minutes. So if it starts at 10:30, it will end at 11:09. Okay, and then folding takes 20 minutes. So if it starts at 11:10, okay, it will finish at 11:29. Okay, so for the first task alone, for the first load alone, if you see it takes how many minutes? 90 minutes, which is 1.5 hours. Okay, there is no change in the first load, whether it is sequential or pipelined, it is same. The first load's output will come at 1.5 hours. But see the second load, washer is free at 10, 20, 10 or 10:30. It is taking up to 10:29. But by 10:30 washer is free. So the second load can be washed during that time. So 10:30 to 10:59 the second load got washed. Okay. So now, but you cannot start, what is this? Drying you cannot start at 11 because still dryer is not occupied by the first load. It will free only after 11:09. Okay. At 11:10 the second load's drying process can be started. Okay, it needs 40 minutes, so it will end at 11:49. Okay, fine. And folder is free at 11:30 itself. It completed at 11:29. 11:30 itself it is free. Actually it is waiting for the job. So but here the drying for the second load is completed only at 11:59, so it can start folder at only 11:50. Now folder is available, so it can proceed with folding. So this will complete after 20 minutes, which is 12:09. Okay, now if you see the difference between time of completion between the first load and the second load. First load completed at 11:29, second load completed at 12:09. So the difference is only 40 minutes. You getting? The difference is only 40 minutes. Okay, so it means this is completed in 1.5 hours. The second load was completed at 2 hours 10 minutes. Okay, 2 hours 10 minutes. Okay, are you getting? Now for so the difference between the first and the second output is only 40 minutes. Now after next 40 minutes the third output will come. See, 12:09 plus 40 is nothing but 12:49. Okay, that is at 2 hours, what you call, at yeah, at 2 hours, at uh, next 40 means 2 hours 50 minutes, right? 40 plus 10 50. At 2 hours 50 minutes the next output will come. Okay, you can figure out this is same as we have discussed. Okay, similarly in the next 40 minutes the fourth load will be completed. So if you add 40 minutes to this, it is nothing but 3 hours 3.5 hours, 3 hours 50 minutes. Okay, 3.5 hours. So now the total time required is only 3.5 hours, because here we are doing pipelining. Here we are doing pipelining. Okay, so this is how the basic concept of pipelining works, right? Now this idea was inculcated into computer science, right? Fine. Okay, so but so let us understand uh, some basic principles about pipelining. Okay, so pipelining will not doesn't help to improve the latency of a single task. What is latency? Latency is the time duration required to perform one task. Okay, latency is the time required to complete one task. Okay, say for example in a processor 1 a task is completed in 20 minutes. Okay, then and in a processor 2 if a task is completed in 10 minutes, okay, then processor 2 is better than processor 1. Our objective is always to decrease the latency. If you decrease the latency, performance will improve. Latency is the time duration between uh, job submission and job completion. That's it. Okay, or the elapsed time between submission and completion. Okay, so but you should understand thoroughly, pipelining is not improving the latency, but it helps to improve the throughput. Okay, so latency is for reducing the time duration required for one job, that is called as latency. So pipelining is not helping us to improve the latency. If you take these two things, this is improved latency, this is not an improved latency. Okay, so pipelining is not improving the latency, but it is going to improve the throughput. Okay, the pipelining rate will be limited by the slowest pipeline stage. Okay, pipeline rate means what? The rate at which it produces the output. See, here you see the rate. So the first output it came at 1.5 hours, but next every output it comes after 40 minutes. Why is that 40 minutes, you may ask? Okay, the next output it came at 2 hours 10 minutes. Okay, 2 hours 10 minutes. Okay, so there is a difference of 40 minutes. Next also there is a difference of 40 minutes. It came at 2 or 50 minutes. Okay, next also a difference of 40 minutes, it came at 3.5 hours. How is this 40 comes? This 40 is nothing but the time required by the slowest device. Here, which is the slowest device? This is the dryer is the slowest device, which takes 40 minutes. Okay, so the rate at which the output comes, that is controlled by the slowest device. Okay, here rate is what? After 40 minutes, leave the first output. Okay, after first output, all the other output comes after 40 minutes. Second output comes after 40 minutes. Third output comes after 40 minutes. Fourth output comes after 40 minutes. Even there may be 100 loads. All outputs, the difference between the previous output and the current output will be 40 minutes. And that is controlled by what? That is controlled by the slowest pipeline stage. Okay, pipeline rate is limited by the slowest pipeline stage. These are the stages. Okay, in this pipeline, these are the stages. Washing is one stage, drying is another stage, folding is another stage. Okay, right? Fine. So basically what pipelining is doing is it is performing more than one task simultaneously by effectively utilizing the resources. Okay, so you can see here what it is doing. While when the first load is drying, the second load is getting washed. That is what is happening. Okay, right? When the second load is when the first load is getting dried, okay, sorry, when the first load is getting folded, during that time the second load is getting dried. Okay, like that it is basically uh, we are multitasking. We are actually performing more than one task simultaneously. Okay, so so more than one unit is used at the same time. Okay, when the first job when the first load is in dryer, the second load is also washing. Okay, when the first load is in fold, the second uh, when the first load is in fold, okay, if you see, that is 11:10. During this time the second load is in dryer. Okay, 11:10 it started. Okay, right? So like that there are multiple jobs are getting executed at the same time. Okay, so so basically this is what pipelining does, so that so that the throughput is getting improved. Okay, right? So the potential speed up of the pipeline will be proportional to the number of stages. Okay, different pipeline will have different stages. Okay, this is, in this example there is three stage: washing, drying, and folding. Okay, so the speed up will be equal to the will be proportional to the number of stages. Okay, and unbalanced lengths of pipeline stages reduces speed up. This is also one of the reason. Unbalanced lengths of pipe stages, which means here actually if you see it is a little unbalanced only. For example, if you see, washing take 30 minutes, drying take 40 minutes, and folding take 20 minutes. It is unbalanced. If it is balanced, means everything will take equal time. Washing will take 20 minutes, drying take 20, and folding also take 20 minutes. That is balanced. Okay, in that case the performance will be better than the unbalanced one. Okay, unbalanced lengths will reduce the speed up to a certain degree. If it is balanced, no, it won't reduce the speed up, because every stage is well defined. Okay, here why we say like that means, here you see, even though the second load it has finished washing at 10:59, by 11 o'clock onwards it is free, but dryer is not available. Are you getting? Dryer is not available. Okay, so uh, 10:59, but dryer is available only at 11:09, so it is waiting for 10 minutes. If dryer takes only 30 minutes, let us assume dryer takes only 30 minutes, then what will happen? Dryer will complete here at 10:59. Okay, 10:59, then dryer would be available immediately when here washing is completed. So from 11 onwards, the second job's dryer would have started, if it is both are of what you call same timing. Okay, right? So that's what we are discussing here. Okay, that is, unbalanced lengths of pipelining will reduce the speed up. Okay, if they are balanced, then that will increase the speed up. Stall for dependencies. Okay, that we will discuss in the future slides. Okay, right now we'll keep this in pending. Okay, so this is the basics about pipelining, right? I think you got the point. So the key takeaway is, pipelining concept will increase the throughput of the processor, but it won't improve the latency. Latency is the time required to execute a single instruction. Okay, if the time required to execute a single instruction is reduced, then we say that it is a better or improved latency. Okay, but with pipelining we are not working on latency, rather we are working on throughput. How we are doing that means, by effectively utilizing the resources, and by making sure that the resources perform more than one task simultaneously. Okay, right? So the speed up of the pipelining will be proportional to the number of stages. Okay, right? So with this we will actually enter into the topics like how pipelining is used in computers, right? Okay, so as we discussed, the stages in the pipeline will differ. The stages in the pipeline will differ. So let us start with a simple case. So let us take a typical processor has two stages of pipeline. A typical processor has two pipeline stages. What are they? One is fetch, the other one is execute. Okay. A typical processor has two pipeline stages. One is fetch, the other one is execute. Okay. So so this is, it is shown here. So there is a fetch unit. This is a separate hardware unit, and there is an execution unit. Okay. The fetch unit is used to fetch the instruction. Okay, the fetch unit is used to fetch the instruction and keep it in the buffer, right? So once that instruction is fetched and kept it in the buffer, the execution unit's job is to take that instruction from the buffer and to execute it. Okay, these two are separate units. Okay, now let us see that, let us say that there are three instructions to be executed: instruction 1, instruction 2, and instruction 3. Okay, if you are executing these instructions without using a pipe, without using pipelining concept, then how many clock cycles it will take? Let us see. So first instructions will be fetched during the first clock cycle, it will be executed during the second clock cycle, and second instruction will be fetched during the third clock cycle, it will be executed during the fourth clock cycle, and third instruction will be executed fetched during the fifth clock cycle, and it will be executed during the sixth clock cycle. So these are the clock cycles: 1, 2, 3, 4, 5, and 6. Okay, so it means what? The instruction, first instruction is fetched and executed, second instruction is fetched and executed, third instruction is fetched and executed. Okay, so each instruction, uh, here we are doing it sequentially. So totally it has taken how many clock cycles? 6 clock cycles. Okay, but if the same thing is pipelined, if it is pipelined, then what will happen? First instruction is fetched during the first clock cycle, it is executed during the second clock cycle, that is by the end of second clock cycle first instruction is finished. Okay, that is same time irrespective of whether it is what do you call, sequential or pipelined execution. Okay, now the second instruction is fetched during the second clock cycle by the time when the first instruction is getting executed or getting, because now the fetch unit is free. Who is doing? Only the execution unit is busy, only the instruction 1 is using only execution unit, fetch unit is free. So instruction 2 can be fetched during the second clock cycle itself. Okay, and it will be executed during the third clock cycle, right? And during the third clock cycle again fetch unit is free, so instruction 3 can be fetched and it can be executed during the fourth clock cycle, right? So what happens now? Now with pipelining, 3 instructions is completed in just 4 clock cycle, in just 4 clock cycle. Let us go further. If there is another instruction I4, what it will, when it will start, it can be fetched during the fourth clock cycle and it can be executed during the fifth clock cycle, that is F4 and E5. Okay, if there is another instruction, say I5, okay, it can be fetched during the, what you call, it can be fetched during the fifth clock cycle, right? It can be fetched during the fifth clock cycle and it can be executed during the sixth clock cycle, it can be executed during the sixth clock cycle. Okay, and so on and so forth, right? So you can see the throughput is increasing. Otherwise, if you are executing 5 instructions sequentially, then we need how many clock cycles? We need 10 clock cycles. But here we are completing 5 instructions in just 6 clock cycle. Okay, right? Okay, 6 instructions can be completed in 7 clock cycles. Okay, if you want to execute sequentially, 6 instructions will need 12 clock cycles. Okay, so on and so forth. Okay, you can keep calculating, right? Okay, so so this is the basics of pipelining, right? Okay, so basically the improvement that can be achieved by the pipelining it will be actually a factor of the number of stages. It will be actually a factor of the number of stages. Okay, that we will try to understand here. Say in this case, what we have seen, fifth instruction is completing at what clock cycle? Fourth instruction is completing at fifth clock cycle. Fifth instruction is completing at sixth clock cycle, right? Okay, so it is just that instruction plus one. One is completing at second clock cycle, second is completing at third clock cycle, third is completing at fourth clock cycle, fourth is completing at fifth clock cycle. Okay, say let us go to instruction 20. So instruction 20 will be completed at 21st clock cycle, right? Because if you follow this logic, first instruction is completed at second clock cycle, second instruction is completed at third clock cycle, third is completed at fourth clock cycle, fourth is completed at fifth clock cycle, fifth is completed at sixth clock cycle, sixth will be completed at seventh clock cycle, seventh will be completed as eighth clock cycle, eight will be completed as ninth clock cycle, ninth instruction will be completed at 10th clock cycle, so on and so forth. 20th instruction will be completed at 21st clock cycle. Okay, now if you see, if you execute 20 instructions sequentially, then you need how many clock cycle? 40 clock cycles. You need 40 clock cycles. Are you getting? 40 clock cycles. Okay, so 40 by 2 is what? 40 by why 2? Because number of stages here is what? 2. Okay, so 40 by 2 is 20, right? So here for 20 instructions we need 21 clock cycles. It is approximately equal, right? So that we have discussed that the improvement of pipelining will be a factor of the number of stages. Okay, right? As you increase the number of instructions, it will come close to 20, right? Let us say 200 instructions. 200 instructions will be completed at which clock cycle? 201 clock cycle. Okay, but if you execute 200 instructions sequentially, then it will complete at which clock cycle? It will complete at 200 into 2, 400 clock cycle. Okay, if you 400 by 2 is 200, which is very near to this, right? Okay, so that's what the concept. It will be the performance improvement will be the factor of the number of stages in the pipeline. Okay, fine. Now let us try to understand a four-stage pipeline. Okay, now let us try to understand a four-stage pipeline. So here we have four stages. Fetch, the processor has four stages: fetch, decode, execute and write. Okay, during the fetch stage the instruction will be just fetched. During the decode stage the instruction will be decoded and the operands will be fetched. After decoding, some input, some source operand or destination operand. Source means the input operand, destination means the output operand. All those things will be fetched and then the instruction will be executed. Then the result will be returned either to some memory location or to register. Okay, these are the four stages in the pipeline: fetch, decode, execute and write. Okay, so let us assume that each stage requires one clock cycle. Each stage requires one clock cycle. Okay, now instruction 1, during the first clock cycle it is fetched, during the second clock cycle it is decoded, during the third clock cycle it is executed, during the fourth clock cycle the output is returned to the memory or register. Okay, and instruction 2, all these are instructions of the same program, let us assume. Okay, instruction 2, it can be fetched, it cannot be fetched during the first clock cycle because first clock cycle is being occupied for fetching the instruction by instruction for fetching the first instruction. Okay, so fetch unit is not free during that time, but at second clock cycle fetch unit is free. So instruction 2 will be fetched at second clock cycle, it will be decoded at third clock cycle, it will be executed at fourth clock cycle and the output will be returned at fifth clock cycle. Okay, now coming to instruction 3, you cannot fetch it at first clock cycle, it is not free because first instruction is getting fetched. During the second clock cycle second instruction is getting fetched. During the third clock cycle fetch unit is free, so instruction 3 can be fetched during the third clock cycle, it's decoded during the fourth clock cycle, it's executed during the fifth clock cycle and the output is returned during the sixth clock cycle. Okay, and instruction 4, fetch unit is during the first clock cycle, fetch unit is with CPU, I mean instruction 1. During the second clock cycle, fetch unit is with instruction 2. During the third clock cycle, fetch unit is with instruction 3. During fourth clock cycle, fetch unit is free. So it can be used to fetch the fourth instruction. Then it is decoded during the fifth clock cycle. It's executed during the sixth clock cycle, and the result is returned to the register or memory during the seventh clock cycle. Okay, right? So this is so here you can see 4 instructions we have completed by the end of 7 clock cycles. To complete 4 instructions, we have taken only 7 clock cycles. Okay, if you are not using pipelining, then to complete these 4 instructions, how many clock cycle will require? For each instructions you need 4 clock cycles. So to complete 4 instructions, you need 4 into 4, 16 clock cycle. Okay, from 16 clock cycles it is reduced to 7. Okay, right? Here the factor of improvement will be up to 4. Okay, that is the maximum factor of improvement possible. Okay, you can check out with larger numbers, right? See here also you can see first instruction is completed at fourth. So just 4 minus 1 is what? 3. So or you can say 1 plus 3 is 4. First instruction plus 3 you add. That is what the result is. It is completed at fourth clock cycle. 2 plus 3 is 5. It is completed at fifth clock cycle. 3 plus 3 is 6. It is completed at sixth clock cycle. 4 plus 3 is 7. It is completed at seventh clock cycle. Okay. So if you take 100th instruction, it will be completed at which clock cycle? 103 clock cycle. 103 clock cycle. Are you getting? It will be with pipelining. I am saying with pipelining it will be completed at 103 clock cycle. Okay. So without pipelining, for 100 instructions you need how many clock cycles? You need 400 clock cycles. Okay, without pipelining for 100 instructions, because each instructions need 4 clock cycles. Okay, so we need 400 clock cycles. 400 clock cycles. Okay, so now if you divide 400 by 103, now if you divide 400 by 103, what you get is 3.88. Okay, if you divide 400 by 103, then the result is 3.88. Okay, which is close to what? Which is approaching 4. Which is approaching 4, because we have discussed, the factor of improvement by using pipelining will be equal to the number of stages. Okay, 3.88 is close to 4, right? Still if we increase, say if you take 200th instruction will be completed at what clock cycle? 203 clock cycle. Okay, with pipelining. Without pipelining it will need how many clock cycle? 200 into 4, that is it will need 800 clock cycle. Okay, now if you divide 800 by 203, if you divide 800 by 203, it is 3.94. Okay, if you divide 800 by 203, it is 3.94. Okay, so the factor of improvement is what? Close to 4. It will not cross 4. Okay, there is no way. Are you getting? So you can work it out, right? So just I am trying to explain that point, which we discussed, that the factor of improvement by using pipelining will be a factor. The amount of improvement in the performance by using pipelining will be a factor of the number of stages. Okay, right? So there will be a buffer in every stage. So after the fetch unit will fetch the instruction and it will keep it in the buffer B1. Okay, from buffer B1 the decode unit will take the instruction and it will decode it. Okay, and it will decode and it will keep the decoded instruction in B2. Okay, in the buffer 2, and the execution unit will take the thing from buffer 2 and it will execute. Okay, whatever the result which comes out of the execution unit, that will be kept in buffer 3, and the write unit will take the content from the buffer 3 and it will write to the appropriate memory location or to the appropriate registers. Okay, so there are 3 buffers, B1, B2 and B3. Okay, fine, right? So now let us try to understand the importance of cache with respect to pipelining. Okay, so See, each pipeline stage is expected to complete in one clock cycle. See here we in the two cases what we have discussed, we just assumed that every stage requires only one clock cycle. That is, fetch requires one clock cycle, execute requires one clock cycle. All these things we assumed. Okay, but this is one of the requirement of the pipelining also. That is, each unit should take exactly one clock cycle. Okay, but actually, if you see, the operation performed by each unit are different. Operation performed by each unit are different. One unit performs fetch, another unit perform decode, another unit perform execution, another unit perform write. So you cannot always ensure that its duration will be same. Its duration may differ, but the requirement of the pipelining is that each unit should take only one clock cycle. Then what should we do? Then we should increase the clock cycle duration such a way that to fit the slowest unit. Okay, like how we discussed in synchronous bus, where the task or the read or write operation should be completed in one clock cycle. So, so we made the clock cycle large enough to fit the complete to ensure that slowest device also can complete within that time. So same thing here also. Let us, for example, assume that the execution unit is the slowest unit. Okay, and say execution unit takes at most maximum it takes uh, 3 nanoseconds to execute. Okay, remaining all instructions, remaining all stages are faster. Now your clock duration should be at least 3 nanoseconds. Now the clock cycle, I mean the clock cycle duration should be, one clock cycle duration should be at least 3 nanosecond. Okay, because the clock cycle for all units should be same. Okay, so in that case the faster unit can wait, the faster unit can wait, but the slower unit, but you should ensure that the duration is enough for the slower unit to complete the task. Are you getting? So that is what we are discussing. Each pipeline stage is expected to complete in one clock cycle. Okay, the clock period, so the clock period should be long enough to let the slowest pipeline stage to complete. The faster stages can wait for the slower devices to complete. Okay, right? Now there is one important thing. So far we have discussed fetch. Fetching means what? Fetching means we are fetching instruction from where? So actually here we are talking about fetching instruction from cache. And also we are assuming that it is an internal cache. Internal cache means it is inside the processor. Here we are assuming that it is fetching the instruction from the cache, and also it is from the internal cache. Internal cache is the one which resides inside the processor. Okay, so that cache can be accessed in no time. It is as if it is with the processor. So processor can access it with very less or with negligible time. Okay, but assume that the instruction is not in the cache, there is a cache miss. Then what will happen? The instruction has to be fetched from the main memory, but accessing the instruction from the main memory will be very slow. It will take more than, surely it will take more than one clock cycle. Okay, it may take 2 or 3 clock cycles, or sometimes it may take 4 clock cycle also. Are you getting? So now the point is, if there is no cache memory, if there is no concept like cache memory, then what will happen? Every time the instruction should be fetched from main memory, which will take around 3 to 4 clock cycles. Okay, then actually the concept of pipelining itself will not be useful at all. Are you getting? So but fortunately we have cache. So most of the instructions will be available in cache. So instruction fetch can be completed in one clock cycle. Okay, so that's what we are discussing here. If each instruction needs to be fetched from the main memory, then the pipeline is almost useless. But fortunately we have cache, so every time you need not go back to the main memory to fetch something. Most of the time it will be available in the cache memory. Okay, so that is the role of cache. So it means without cache, pipelining is not possible. If cache memory is not there, then there is no pipelining, because then every time you have to fetch from main memory, that itself take 3 or 4 clock cycle. Then if the fetch itself delayed, then obviously other operations like decode, execute and write, everything will be delayed. Okay, right. Okay, the potential increase in the performance of the pipelining will be proportional to the number of stages. That's what we have discussed with some examples and all. Okay, the performance improvement in the pipelining will be proportional to the number of stages. Okay, so but there is another thing. This increase is achieved only if all pipeline stages requires the same time to complete. Okay, so now we are going to go to the next level of pipelining. See here, all these places we assumed that all, and also we discussed that pipelining, each stage should be completed in one clock cycle. Okay, and we ensured that the clock cycle duration will be equal to that of the slowest stage. All these things we assumed, we discussed, and also we discussed that uh, whatever we have discussed here we assume that everything is just completed within one clock cycle. Okay, that is, everything is going on perfectly. Okay, so only if it is going on like this perfectly, then only this performance improvement logic is applicable. What performance improvement logic? That is, the performance improvement in a pipeline will be proportional to the number of stages. Okay, that will be applicable only if every instruction is completing like this. Say I said that fourth instruction is completed at seventh clock cycle, and also we said that then 200th instruction will be completed at 203 clock cycle. Okay, it means it means we are assuming that nowhere no problem is happening, everything is going smoothly. Okay, but in reality that is not the case. In reality that is not the case. Somewhere some mishap may happen. So that's what we are going to discuss next. Okay, so this increase in the performance, that is, what increase in the performance? The increase in the performance will be proportional to the number of pipeline stages. Okay, if the execution is continuing in this order, that is, if each instruction, that is, if each phase is exactly taking one clock cycle, and like that you are continuing for so many instructions, then obviously the performance improvement also will be proportional to the number of stages. Okay, but in reality uh, but in reality this is not true. Okay, so this increase can be achieved only if all pipeline stages require the same time to complete. That is, everything should require only one clock cycle, nothing should be delayed. Then only we can ensure that this performance increase. What performance increase? Which is equal to the which is proportional to the number of pipeline stages, right? But it is not possible if 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 any of the stages requires more time. Okay, during any during execution of any single instruction also, then also you cannot match uh, to the proportional of the, what you call, to the proportion of the pipeline stages. Okay, right. So now let us discuss one example for that. So, right, so again this is a four stage pipeline. See, instruction 1 is fetched during the first cycle, it's decoded during the second cycle, it's executed during the third cycle, and the output is returned during the fourth clock cycle. Everything went on fine. Coming to instruction 2, it is fetched during the second clock cycle, it's decoded during the third clock cycle, its execution, which is supposed to be completed during the fourth clock cycle, it got delayed by 2 clock cycles. Okay, due to some reason, whether it may be any reason. Okay, anything may happen. Our upper bound is we are trying to complete by 1 clock cycle maximum, but this will happen at some times. So instruction 2, it is supposed to be complete, execution should be completed at 4th clock cycle, but actually it is completing at 6th clock cycle. Actually it is completing at 6th clock cycle. So its write will be delayed. So by the 5th clock cycle, its write will be postponed to 6th clock cycle. Again at 6th clock cycle also execution is not completed. So again write will be postponed to 7th clock cycle. Okay. So write is completed at 7th clock cycle. So instruction 2 now completed at 7th clock cycle. Actually it is supposed to complete at 5th clock cycle. Are you getting? Right? As instruction 2 is delayed, other instruction also should be stalled. This is called as stalling. Before that we discussed, right? Stalling means stopping. Okay. Here instruction, see, when instruction 2 is executing, instruction 3 can be decoded, that is fine. Okay, but now instruction 3 is decoded, but you cannot execute this instruction 3 because instruction 2's execution is not completed, because we are assuming all these instructions are from the same program. Okay, so instruction 3 execution may depend on instruction 2. Okay, instruction 3 execution may depend on instruction 2. So until instruction 2 has finished executing, you cannot execute instruction 3. So instruction 2 has not yet finished. Okay, so instruction 3 has to wait until instruction 2 finishes execution. Then only instruction 3 can execute, and then the output will be written. Okay, so instruction 3 is now completing at 8th clock cycle. Otherwise it is supposed to complete at 6th clock cycle. Okay, now not only instruction 3, instruction 4 is also stalled. Instruction 4 is fetched during the 4th clock cycle. Okay, now now it's not even decoded, it is stalled. It is stalled because instruction, what you call, instruction 3 is not completed. Okay, instruction 3's execution is pending. Instruction 3's execution is pending, so it is stalled. It is stalled for 2 clock cycle. Okay, once once instruction 3 starts executing, see, you may ask like, why it is not decoding. Okay, that is a good question. Why instruction 4 is not decoding? Instruction 3 has decoded, right? See, before completing this execution, instruction 3 has decoded. But why instruction 4 is not decoding? See, instruction 3 has decoded because instruction 2 has started executing. Instruction 2 was started executing. Okay, it is not that it is not executing, it is started executing. So if instruction 2 started executing, then you can decode instruction 3. Are you getting? But here what you see, instruction 3 is not started executing. Currently which instruction is executing? 2 is executing at this time. Okay, so you even if you decode instruction 4, you may need something from instruction 3 also. An output of instruction 3 also may be required. So there is no point in decoding. Are you getting? So this decoding is delayed. Are you getting? So you can took it this way. Instruction 3, instruction 4 decoding is delayed because instruction 3's execution is not even started. Okay, only when instruction 3 execution started, instruction 4 can be decoded. Okay, so its decoding is delayed. When instruction 3 execution starts, then instruction 4 decode started. Are you getting? And then it executes and then it writes. So it is completing at 9th clock cycle. Okay, otherwise it should be completed at 7th clock cycle. Okay, similarly instruction 5, if you see, it is not even fetched. Its fetching is delayed to 7th clock cycle. Its fetching is delayed to 7th clock cycle, and it is decoded and then it is executed. Okay, so it will complete at what do you call 10th clock cycle. Otherwise it is supposed to complete at 8th clock cycle. Okay, so now all instructions are delayed by 2 clock cycle. Instruction 2, which is supposed to complete at 5th, it is completing at 7th. Instruction 3, which is supposed to completing at 6th, it is completing at 8th. Instruction 4, which is supposed to complete at 7th clock cycle, it is completing at 9th clock cycle. Instruction 5, which is supposed to completing at 8th clock cycle, is completing at 10th clock cycle. Okay, so now all instructions are delayed by 2 clock cycles. Okay, right? So there are two things. One is delay, the this instruction 2 is delayed. Okay, this is delayed by 2 clock cycle. These things are stalled. This is stalled. They are, that unit itself is stalled. Okay, instruction 3 is stalled. Instruction 4 is stalled by 2 clock cycle. Instruction 5 is also stalled. Okay, by 2 clock cycles. Are you getting? Okay, so this is how it works, right? So the previous pipeline, whatever we have seen, it's said to have been stalled for 2 clock cycles. Okay, any condition that causes a pipeline to stall is called as hazard. This is another important term with respect to pipeline. Okay, any situation that causes a pipeline to stall, because of some situation, if the pipeline stalls, then that is called as hazard. There are 3 types of hazard. One is called as data hazard, the other one is called as instructional or control hazard, The other one is called a structural hazard. What is data hazard? Data hazard happens if a data is not available. Okay, if the pipeline gets stalled because of the unavailability of a data. Okay, that is some source operand. Source means input operand, or some destination or output operand is not available. In that case, if the pipeline is stalled, then that is called as data hazard. Okay, so any condition that leads to stall is called as hazard. This hazard can be of three types: data hazard, instruction or control hazard, and structural hazard. What is data hazard? If the pipeline is stalled because of unavailability of source or destination operand, then that is called as data hazard. Okay. If the pipeline is stalled because of the delay in the availability of an instruction is not available. The next instruction to be fetched is not available in the memory, in the cache. So if it is not in the cache, what will happen? It has to fetch from the main memory. So that will take more time. Okay, so because of that also hazard will be created. Are you getting? Normally instruction we will fetch from cache memory. If there is a cache miss occurs, then you have to fetch it from main memory, which may take 3 or 4 clock cycle. So during that time there is a hazard. Okay, that hazard is called as instructional hazard. The third hazard is called as structural hazard. Structural hazard means sometimes you may not have that particular hardware may not be available to perform that operation. That is called a structural hazard. Data is available, instruction is available, but that hardware unit to perform that operation is not free. Okay, that is called as structural hazard. The situation when two instructions require to use the same hardware. Okay, at that time structural hazard will occur. Okay, say for example instruction 1 is in fetch stage. Okay, it is fetching from main memory. Say there is a what you call, there is a catch miss, so it is fetching from main memory. At the same time, say instruction 2 is in, this is instruction, say some other instruction, say instruction 3 is in fetch stage. Okay, at the same time, say instruction 1 is in execute stage, and it also want to access the main memory, same location. So which location instruction 3 is accessing in the main memory, the same location instruction 1 also want to access. So that type of hazard is called a structural hazard. Now one of that will be delayed. Are you getting? That is, two instructions would like to access the same hardware resource at the same time. Then it will lead to structural hazard. Fine. So let us see in the previous case what we have discussed. This hazard, actually this is a data hazard. This is a data hazard. Why we call it as data hazard? What is first of all hazard? If the pipeline is stalled due to some reason, then that is called as hazard. Why this pipeline is stalled? Why instruction 3 is stalled? Because the data is not available from instruction 2. It has not finished execution. Only if it finished execution, the data will be available, then only instruction 3 can execute. Okay, right? So as the data is not available, this is called as data hazard. As the data is not available, because of that the stall is created, so it is called as data hazard. Here is an example for instruction hazard. Instruction 1 is fetched during first clock cycle, it is decoded during first clock cycle, it's executed during first clock cycle, and it is returned to the memory. Fetched during first clock cycle, decoded during second clock cycle, executed during third clock cycle, and returned to the memory or register during fourth clock cycle. Now coming to instruction 2, it is supposed to finish fetching by second clock cycle. But what happens? That instruction is not available in the cache. So there is a cache miss. So it should be fetched from the main memory. For fetching from the main memory, it took another 3 clock cycle. So totally it took 4 clock cycle. Okay, so fetching is now completed only at 5th clock cycle. Fetching is now completed only at 5th clock cycle. Okay, so what do you call? It's decoded at 6th clock cycle, executed at 7th clock cycle, and return the result at 8th clock cycle. Okay, now instruction 2 actually it is supposed to complete by 5th clock cycle, it is completing at 8th clock cycle. So there is a stall for 3 clock cycles, and this stall will continue. Instruction 3, which is supposed to complete at 6th clock cycle, now it is completing at 9th clock cycle. Okay, so this is, here a stall is created, here a stall is created for all the, for instruction 3, 4 and everywhere. So this stall is created because of the not availability of the instruction. So this is called as instruction hazard. Okay, so this diagram is nothing but another way of representing the pipeline. Okay, instead of drawing diagram like this, we can also show like this. This is the clock cycle, this is fetch, this is decode, this is execute, this is write. During the first clock cycle, instruction 1 is fetched. Okay, during second clock cycle, instruction 2 is fetched, but instruction 2 is getting fetched from second clock cycle to fifth clock cycle. Here you can see, so F2, 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 F2 is there, and instruction 3 is fetched during the sixth clock cycle. Are you getting? Instruction 1 is decoded during the second clock cycle. Okay, right? During the third clock cycle, idle, decode unit is idle. Nobody is using the decode unit during the third clock cycle. If you see here, nobody is, anybody is using decode during idle? No. During fourth clock cycle, nobody is using. During fifth clock cycle, nobody is using. During sixth clock cycle, decode is used by instruction 2. Okay, decode, so it is 2 here. 2 represents which instruction is using. During sixth clock cycle, it is used by instruction 2. During seventh clock cycle, decode is used by instruction 3. Okay, coming to execute unit, it's first used in third clock cycle by instruction 1. Okay, then during instruction 4, during clock cycle, it is first used by instruction 1 during third clock cycle. During clock cycle 4, nobody is using execute. During clock cycle 5, nobody is using. During clock cycle 6, nobody is using. During clock cycle 7, instruction 2 is using it, execute unit. During clock cycle 8, instruction 3 is using it. Similarly, write, if you see, during fourth clock cycle, it is used by instruction 1, and it is not used during 5th, 6th and 7th clock cycle. It is used at 8th clock cycle by instruction 2, so W2, and it is used in the 9th clock cycle by instruction 3, right? Okay, so it can be represented in this way also. This is just another way of representing. Okay, idle periods are called as stalls or bubbles. So these are the stalls. See, this is called a stall. Okay, this is I2 is not stalling. I2 is waiting, or it is doing, or it is delay. Not waiting, it is delayed. I2 is delayed, but I3, I4, all the further instructions will be stalled. Okay, fine. So this is an example for structural hazard. Here we have an example for structural hazard. Let us see how it works. So we are going to discuss this with an example instruction load x of r1 comma r2. Okay, so it is what we are going to, this instruction, what it does in the sense, it x represents some memory location. Okay, so say for example x represents to memory location 2000, r1 represent some register content. Say if r1 is equal to 25, then what it will do means it will add x plus r1. X plus r1 is what? 2025. 2025. Again, now this 2025 represents some memory location. From the location 2025, whatever the data is there, that will be, a copy of that will be kept in R2. Okay. Okay. If the location 2025, say the location 2025 contains something 100. Okay, then this 100 will be moved to R2. This is what it is going to do. Now we are going to, it will be moved to the register R2. We are going to discuss this example under structural hazard. Okay, fine. So this instruction we are assuming it as I2, instruction 2. Instruction 2 is this. Other instructions we don't know what are they. Okay, this is the load instruction which we are going to discuss. So instruction 1 is perfectly following the flow. Fetch during clock cycle 1, decoded during clock cycle 2, executed during clock cycle 3 and returned during clock cycle 4. Done. Okay. Now during second, the instruction 2, this is which is the instruction which we are discussing. It is fetched during the second clock cycle. It is decoded during the third clock cycle. but its execution, what happens during fourth clock cycle, it is just able to perform this calculation. Let us assume during fourth clock cycle it is just able to perform this calculation. What 2000 plus 25 is what 2025. That calculation alone it completed during fourth clock cycle. Full execution it is not completed. Full execution is what? It should complete this calculation x plus r1, and it should take that data, and that it should take that data, that is called as execution. It should fetch that data. Writing will be done in the final write stage. Okay, then it will be returned to r2. So execution actually includes two things here. With respect to this instruction, execution includes two things. One is calculating this x plus r1 and to fetch this data. So for calculating it, it took one clock cycle. Okay, and for accessing this memory and acquiring this content is what 100. Okay, it acquires this 100 and keeps it some buffer or somewhere. For that it took another clock cycle, which is clock cycle 5. Are you getting? And actual writing of this 100 to r2, actual writing of this 100 to r2, it happened during the 6th clock cycle, right? Fine. So now we can say that this execution is actually these two clock cycles was used for execution. Which clock cycle? Clock cycle 4 and 5. These two clock cycles were used for execution. Okay. During fourth clock cycle, this sum of x plus r1 is calculated. During fifth clock cycle, the content of x plus r1 is fetched. And during the sixth clock cycle, that content, so if you remember, if you recall the what you call the diagram, the stages diagram, there is a buffer. Okay, so what we are saying is during fourth clock cycle, that address, that sum of 2x plus r1 was calculated. During fifth clock cycle, that content was fetched and it was kept in this buffer b3. Okay, this buffer b3, that 100 was located. Okay, and during sixth clock cycle, the output was returned to r2. R2 becomes 100. So this is what has happened. Okay, now that execution is actually elapsed for 2 clock cycle, which is supposed to complete in 1 clock cycle, but actually it has taken 2 clock cycle, right? So the execution is delayed. It took 2 clock cycle. Now what will happen? There will be a hazard. How the hazard? Let us see. Now instruction 3, it is fetched during 3rd clock cycle. It is decoded during 4th clock cycle. It is executed during 5th clock cycle. Okay, because even though here we say that execution is extended, but actually execution unit is free. This second part, this first part is for what? Calculating sum. That is the actual execution. The second part is what? Fetching from memory. So fetching something from memory, that whatever x plus r1 gives, that data should be fetched and kept in the buffer. So during this time E is free, E unit is free, so it can be used by I3, instruction 3. So it finished execution. Are you getting? But now this why there is a stall. The stall why means after E3, what third instruction want to do? It want to perform write operation. So write means again it may want to access some registers, right? But here 6th clock cycle, what instruction 2 is doing, it is also writing to the register R2. So register means one entire set. We call it as register file. Okay, all registers are available in CPU. All these register set is called as register file. Now only one process can access the register file at a time. During 6th clock cycle, already instruction 2 is accessing the register. So instruction 3, now it cannot access the register. So it is stalled. Okay, so this stall happens because of what? It is not because of availability of data. Data is available because execution is completed. Instruction is also available. Which is not available? This hardware resource called register file is not available. As it is being used by some other process or some other instruction, it is not available to instruction I3. So here a hazard or a stall is created, and this stall happened because of the non-availability of the register file, which is a hardware resource. So this type of hazard is called a structural hazard. Okay, so this hazard it propagates. So instruction 4 also, it is fetched, decoded, and and it is not here also it is not executed. This execution is delayed. And similarly instruction 5, okay, instruction 5 also uh, it is the previous instruction is not decoded completely, okay. So 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 its fetch is delayed, okay, and its decode is delayed, okay. So now all instructions, if you see, they are delayed by, they are stalled by one clock cycle. Instruction 2, it is supposed to complete at fifth clock cycle, it is completing at sixth, okay. Instruction 3, it is supposed to complete at sixth clock cycle, it is completing at seventh, right. Instruction 5, which is supposed to complete at seventh clock cycle, now it will sorry, instruction uh, 4, which is supposed to complete at which clock cycle, seventh clock cycle, it is completing at eighth, okay. Instruction 5, which is supposed to complete at eighth, it will complete at ninth clock cycle, okay, right. So this is called a structural assault, right. Fine. So to summarize, pipeline does not result in individual instructions being executed faster. That is, it will not improve the latency. Rather, it will increases the throughput. Okay. Throughput is measured by the rate at which instruction execution is completed. So causes pipeline stall causes degradation in pipeline performance. Obviously, if there are more stall, then the performance will be degraded. Okay. We need to identify all hazards that may cause the pipeline to stall and find ways to minimize their impact. Okay, there are three types of hazards we have discussed: data hazard, instruction hazard, and structural hazard. We need to identify these hazards, and we need to ensure that we should identify the ways to minimize the impact of stalls. Okay, so that we'll be discussing in the coming lectures. Okay, you can try to draw a pipeline stage for this particular question. Consider there are four instructions. Okay, the instruction 2 takes 2 clock cycle for execution. There are four instructions. The instruction 2 takes 2 clock cycles for execution. For this, draw the 4-stage pipeline and figure out the total cycles needed for the 4 instructions to complete. So there will be, the instruction 2 is delayed by 2 clock cycles during execution. Okay. So there will be some stalls in the lower level. So identify that. So and draw that pipelining diagram. Okay. Fine. Thank you. Let us stop here.